Oh. Maybe the adapter's there. Yeah, good.
Thanks. Appreciate it.
Okay. Number 4. Just read it over. Yeah. Okay, we have it's a diving board. I would, if you ever have an object that even looks like there's some sort of beam involved, you know that you have to apply that condition for rotational equilibrium. All the torques should sum up to 0. I would just simplify the diagram and just draw the beam. And that draw the pivots. We put it on the left side, if in doubt, far left side. It's attached to the wall on the right. Similarly, put it on the right. Unless otherwise told. So this is 99% of the cases where we place it on the left side. And just draw in the forces involved. So we have, there is a force acting, I would say it's probably down to fasten that end so it doesn't pop up. There's a force acting up by this second pillar. I'll call this F1, and this is F2. And then there's a force of gravity that's acting at the center of the beam, Fg. And then there's the force on the diver, call it Fd. Okay, and then the corresponding length, they don't give us the length, they just state it's L, which is fine. As long as we've got the distance between, so the distance between, put this in red here, the pivot and F2 is 1/4 of the length. Right? The length of the beam they just called L. And of course, Fg is going to act at half L. Okay, now the other point is, before we begin, this will help us simplify the torque expressions. The angles are all 90 degrees. Okay, that means that our expression is going to simplify. The sine of 90 in each of those cases is 1. Yes?
Why did you draw F1 below the board and F2 above the board?
Well, yeah, I'm not sure which direction this is. can draw it up if you want. There's two pillars, right? So obviously there's a force that's related to each of those pillars. They ask us for that, F1 and F2. You could draw whatever direction you want. If you get it wrong, if your direction that you drew is wrong, you'll just get a negative answer. It's fine. I suspect, though, physically speaking, that it's down because if you've got a diver here, that's going to push, if this is the pivot, that'll push the beam, rotate it this way and pop this end up. So the only way to make sure it doesn't pop up is to have a force acting down. It could be like a nail or a screw into the pillar. So we'll see. If my assumption's right, then I'll get a positive answer. If I'm wrong, I get a negative answer. I just have to mention that. Okay, good question. Okay, so let's just label each of these. Now, there is no torque due to F1. That's the whole point of putting the pivot on the left side there. It eliminates the torque due to the forces at that endpoint. So there is a torque 2, and that's equal to F2, which we don't know, but we'll find, times the sine of 90, because it's perpendicular, times a quarter L. And this just simplifies to F2 times a quarter L. The sine of 90 obviously is 1. That's my torque 2. My tau G, my torque G, is Fg times the sine of 90 times 1/2 L. And this just simplifies to Fg half L. Now, let's see if we can, before we can, do we have any other information here? The uniform, well, we know it's, let's simplify it further because we know Fg is 400. So let's write that in. 400 times half L. So it simplifies to this 200 L. Okay. The force on the diver is mg 75 times 9.81. So let's make sure we figure that out before we write down that torque equation. So that works out to be 736. Okay, now we can go up here. The torque on the diver is 736. Because that's what the force is. Times the sine of 90 times L. And this just simplifies to 736 L. So I just wrote down the absolute values. Personally, you can do however you want, but I like adding the sign in later, right? After the fact. I like just writing down the calculations. I can insert the sign after. So let's do that. We have to remember, we have to now ask ourselves the question, which ones are the negative torques? Where do I have to add a negative? Okay, this is the pivot. It doesn't move. So this beam can rotate this way, clockwise or counterclockwise, with that pivot remaining at the same position. So these two forces would result in a clockwise torque. They're going to be negative. That's where I insert my negatives. You can insert it here, or you can insert it later on in the equation, however you prefer. Just make sure that you take into account a clockwise torque. This force here would rotate the beam, again, with the fulcrum or pivot stationary, would rotate it this way. It's counterclockwise. So that's going to be positive. Don't have to add anything. So what do we have for the sum of the torques? Sum of the torques is 0. We have tau 2 plus tau G plus tau D. Remember that these last two are negative, so the negative is there. We can just write in the expressions. It's going to be negative. There's a common factor in each of these. In each term, there's a common factor L, which will divide out. You don't have to do all these steps. I go the extra mile for you for clarity's sake, for those who may not have followed all the steps. You have to show some work, though, obviously. I'll carry an extra digit because we probably need it later on. We need it in another step. So yeah, it's 3.7 times, it's 3,700 newtons. And notice I get a positive answer, so I assumed it was up. It is up. It is up. I would put that in there. A little less finicky with an assignment with the test. Make sure you indicate the direction, yeah. I need to either see it in the diagram or I need to have it stated, the direction. I'm looking for one of those two. So I would still, even though it's a test, you're trying to save time, I would still draw the diagram. Yeah, more? Which 400?
Oh, that's just the weight of the board.
Oh, it's given, yeah, 400 newtons. Okay, this is just part, it doesn't divide it up, but it does ask you what are the forces acting on each support. I only found F2. I need to go back and find F1. So that's the second part. There is two parts to this question. Second part, find F1. What's the trick to that? Well, I now have F2. The trick is, in a second part of an equilibrium problem, of a rotational equilibrium problem, use this fact. Sum of the forces in the y and x. I don't have any x in this equation, so I'll just use the y's. They balance. The forces balance. Okay? So what are those forces? That's why the diagram's helpful. Let's just revisit it. I've got F2 that's acting up. I'm assumed F1's acting down. FG is acting down. FD is acting down. Anything acting down is going to balance whatever's acting up. So you've got F2, it's going to be positive, minus F1, minus FG, minus FD, 0. Just what I said. This is just saying mathematically the upwards forces are balanced by the downwards forces.
This is like they're not affected by like lever length or.
No, just an experimental fact. Interesting. Okay, so did I make a mistake here? I gotta solve for F1. That's my mistake. I gotta solve for F1. I've got F2, I've got this. I've got to solve for F1. Top equation's correct. So is the bottom, but I want to rearrange for F1, so let's do that. F2 minus FG minus FD is equal to F1. FG we said was 400. FD we said was 736. So works out to be 2.6. Okay, and it is down. I got a positive answer, which means my direction that I assumed is correct. It's down. If I got a negative answer, then you'd have to interpret it. You have to say, well, it's in the opposite direction that I assumed in the diagram. It's not down, it's up. Okay, 5. Yeah,
So if you originally assume that like the thing was pulling down and you get a negative answer, it's actually going up.
yeah.
Um,
And you got to state it. Yeah.
um,
It is down in this case. Okay, number 5. Oh, interesting. That doesn't help me. Okay, read over 5. I'll draw it for you. Okay, so it's just asking you for the tension in the rope, FT. It's a torque problem. Here's your pivot. Put it here. Length is L. They don't tell you anything, but if in doubt, length is L. This is a half L. Okay, half L. So what are the torques? Just write them in. This simplifies to Ft times a half L. That's the first torque. Second torque, I'll just write down the absolute value, then we'll figure out which ones are negative. Okay, this torque here, the torque due to the weight, rotates it that way, clockwise. So that is the negative one. There's only 2 torques. So they have to balance. Both of them have an L in it. So as I said before, if it's a common factor in each term, it cancels out. And it came out positive. Well, we know what the direction is. The direction is indicated in a diagram. So, yeah, draw the diagram with these as I have set it up. Set it up in the same way. Six. Read over 6. Fuck. Mm-hmm.
Why are you adding them? Because they're in different directions.
I put, you could put a negative here if you want. You want to do it that way.
It's like adding.
You add the torques, but one of them is negative. It's the same thing. However you want to do it. Just remember there's a negative somewhere. Okay, so this is 50 here. This must be the complementary angle that I just, this one here has to be 40. Complementary, it's complementary to the 50. I'm not done. Don't put up your hand before I'm done, please. Okay, that's 50 here again. This has to be 50. Okay, let's write in our expressions.
Can you scroll down?
Okay, there you go. Better? Yeah. I would use, now here's the thing. This is as before, length L. Okay? People get confused, but you're still measuring the length that the force, the tail of the force is from the fulcrum, from the pivot. So this is still a half L. You're still using that half the distance, even though the beam is not level. This would be a negative torque. $200 Newton. It's a 200 Newton beam. Let's see if we can simplify this. 200, 100 times, what's 100 times sine 40? Let me see here.
64.27.
64.27. Thank you. And this here will simplify here. Sine of 50 is 0.766. Only two torques, so they have to balance each other. This should be it. That should be L. Don't forget your L there. Let me see if I got a show for you. Falling asleep. Okay, so there's an L in each term, cancels out. This works out to be 84. Okay. So just a couple of things to learn from this beam here that's at an angle. Remember, you're still using, for this force, for the weight of the beam, even though it's not acting, it's no longer perpendicular, no longer 90 degrees here, it's 40 degrees. You're still using the distance of 1/2 L, because it's the distance we always use is from the pivot measured parallel to the beam to the tail of the force. Okay, so you can work on your lab, work on that. I also have an assignment I'm going to give out in a minute, so I'll just hand those out, and I'll tell you what questions to work on those. But you can get out your lab, you can work on that now, or you can work on the assignment you're about to get.
Once you use like the sun here, so like the arrow here going down, that's 200, right? Or like the sun, like that would be 200 times half L. But like for the side, what are you getting?
I'm using the angle at the tail.
Oh,
Always use the angle at the tail of the vector. So it is 40 degrees.
so
There you go. Okay, so for the equilibrium assignment, okay, it's due Wednesday. Tests on equilibrium Thursday. Okay, now questions you're going to do all the multiple choice, but show the work. Show work. Okay. Okay, pay attention. You can skip ahead to M26. There's an M26. This is you want to make a note. This is an exception where the weight of the beam is not at the center. And the reason why is because it's not an evenly distributed beam. So make a note of that. They tell you where it's acting at. It's acting at the 3 meter mark. So that's an exception there. Okay. So as far as the written, Written. You can do W1 and W3. And do this on a separate piece of paper. There's just not enough room for work. One more point. Remember, when you're calculating torque, look at this diagram here. Look what I did. You use the angle at the tail of the vector. You have to, and if it's not given, you have to calculate it like I did. I figured it out. It was 40. It's at the tail of the vector. So I took the sine of 40, not of 50. Yes.
What's the percentage at the side of what's called equilibrium package?
That's this is from the old curriculum, so it was 12% of the old curriculum. We've switched over, right? Mm-hmm.
If I start getting this 40-degree angle by using a right triangle formula by adding 90 plus 40.
Yeah, it's 50 here, right? Yeah, just I said it's a complementary because you look at the triangle here, right angle triangle. This side must add up to 90.
Yes.
That was 50. That must be 40. Okay, yeah, if you look at the diagram, that's 50. So that must be 40. Okay? Adds up to 90. Okay, guys, you can get started on that. You got extra time today, so do that. Finish off the lab if you want. Lab due tomorrow morning.